Hello students. So far in module 2, what we have seen is how we have split the instruction execution into 5 steps, distinct steps. One to name: fetch, decode, execute, memory, and write back. Right. After that, we started building the control path and data path, basically at the block level, may not be at the actual circuit level, because that's where our abstraction is in this course. Right now, in the remaining lectures of this course, of this particular module in the course, we are going to look at a very interesting topic, very relevant topic, and uh, I would say the most influential idea in architecture, right, which is pipelining. So if you have noticed in this particular slide, I have used different font sizes. For the pipelining idea itself is very small, and most of you have already grasped it during the module 0 itself, right? But in this few lectures, we are going to see how we can get a pipelined execution of instructions working. Basically, yes, we might know, okay, pipelining will definitely help us, but how do we implement it? What are the practical issues we are going to face when we want to pipeline the instruction execution? That's the reason how to work, or how to get this idea working. I have put it as a bigger font. Basically, that's where the stress would be, right? So even though I've mentioned about pipelining at a very high level earlier, I'll now dig a little more deeper, taking specific example of the assembly line for the automobile manufacturing. Right now, here is my x-axis, which is the time axis, you can say. On the y-axis, we are going to see the progress of individual cars. For example, let's say the first car C1 would take some 24 hours of time to get manufactured. Right after 24 hours, the unit would be rolling out one car, and in the next 24 hours, the unit would be working on another car. Let's say that, let's call it C2. Right, and at the end of second 24 hours, we are going to roll out one another car. The similar thing would happen in the third 24-hour slot also. We are going to work on some new car C3, and we are going to roll out at the end of that 24-hour slot. Right now, if we look at the overall operation, we would call it as non-pipelined operation. We are going to look at why it's called non-pipeline. But if we are going to look at the throughput, how many cars are we able to produce in per unit of time, it would be one car for every 24 hours. Now, how do we improve it? Obviously, we can say that, okay, just like one assembly line, I'll have multiple assembly lines, so that instead of rolling out one car, uh, I can roll out three cars if I have three parallel assembly lines, right? So that is also an interesting method. But look at the hardware overhead that you would need, right? Basically, that approach would be a parallel approach, right? We are trying to get multiple tasks done in parallel, right? But uh, if you ask, isn't that one of the approach? Yes, it is also implemented, but it's a huge cost. Let's look at something more subtle in its again, we are exploiting the parallelism, but in a very subtle way. That's why we call it pipeline. Let's see how it goes. Now, the very first thing that we would do is to identify the entire manufacturing of a car, uh, identify how many subtasks are there, smaller tasks, and which uh, possibly are independent. Now, let's say uh, instead of viewing the entire manufacturing as one single lot, we are trying to visualize it as 4 different parts. Okay, the first part is building the engine of the car. Let's say it takes 6 hours. The second part, or the second step, would be the building body of that car, or building the chassis, right? And the third job would be uh, the painting, and the fourth job, which is very important, is testing the overall working of the car. Let's say, for simplicity, all these tasks are taking 6 hours each. Now if you look at one particular car, it would still take 24 hours to get built, right? And only at the end of 24 hours we can roll it out. But now that we have identified multiple smaller and independent tasks, let's see how we can exploit that. In the first 6 hour slot, when uh, the car C1 engine is being built, we are waiting. But the moment we move on to building the C1's chassis, what we are going to do is we are going to start building the engine of C2, right? In the third 6 hour slot, when C1 is moved to the paint work, what we are going to do is C2 will be moving to the chassis building, and we'll start building the engine for C3. In the fourth 6 hour slot, the C1 would be in its final stage, which is testing. C2 would be moving to the paint, uh, and C3 would be moving to the chassis building, and we'll start working on C4. In the fifth 6 hour slot, C2 would be under testing, C3 would be painted, C4 uh, chassis would be built, and we'll start working on the engine of C5. So this would continue. Uh, so by the end of uh, first 24 hours, right, the first car would be rolled out. But the interesting thing, if we are able to achieve such a pipeline assembly line, is right after the next 6 hour slot, the second car is ready to be rolled out. And after that, 6 more hours, we can roll out the third car. 6 more hours, we can roll out the fourth car. And 6 more hours, we can roll out the fifth car, right? Now, this is called a pipeline implementation, wherein we are trying to overlap the building process, right? Obviously, with overlapping will be of different steps of the car manufacturing, right? Now, the biggest advantage that we would get is the throughput. Earlier, the throughput was 24 hours would be taken to roll one car out, but here effectively we are taking only 6 hours to roll out one car, right? So with not so much additional hardware, we are able to get better performance from this overall manufacturing unit. Performance here would be the number of cars we are building, right? Now let's try to extend the same thing for instruction execution. Okay, if a small point correlating to what the we would be looking at is the cycle time. Earlier, the cycle time can be imagined to be 24 hours, and now the cycle time would be 6 hours. Okay, it's important to note that we still take 24 hours to roll out a car. That is not changing at all, right? We still need to do the same amount of work to build a car, but we are able to work on different cars at different stages. That's where the notion of parallelism is coming in, right? Now let's look at the pipeline assembly line. We already know. Before that, uh, from the unpipelined or non-pipelined version of the assembly line to the pipelined version, we are able to improve the throughput by 4 times, basically because we split into 4 different parts. And each of these parts would be having a dedicated set of workers, means there will be a group of workers who will be just building the engine, group of workers who will be just building the body of the car, group of workers will be there who will be painting, and other another group of workers would be there who will be doing the testing of the car. So let's call them work groups. So all these work groups would be engaged all the time effectively, right? But if you look at the non-pipeline version, during the first 6 hours only the guys who will be building the engine will be working, all the other three groups would be idle, right? In the second 6 hour lot, uh, only those workers who build the car's chassis would be working, and still the other three work groups would be idle. Instead, if we are able to get the other groups working on different cars, we'll make them basically work more efficiently, right? Now in this process of achieving 4 times the throughput, what did we assume? Let's look at those assumptions, because they are very important to address when we want to actually implement the pipelining. The very first one assumption we made was that we are able to split into 4 equal parts in the sense each part of the car manufacturing would still take 6 hours, right? What if they are not equal? We would we still be able to achieve 4 times the speed up or 4 times the throughput? We might not, right? And another assumption we made was making uh, of one car is totally independent of another car. Yes, it might be looking quite obvious for the car manufacturing, but it's not so obvious for instruction execution, because there will be uh, a very common case that the output of one instruction might be used by another instruction. We are going to look at those dependencies, right? What is the third assumption we made? Is that there are sufficient exclusive work groups. It means we have a group of people, uh, each for engine, chassis, paint, and testing. But what if that's not the case? Maybe there is the same group of people would still be doing engine and the paint work. What if that's the case? We will not be able to pipeline them properly, right? So but the 4 times throughput was achieved assuming that there are 4 different work groups. And the fourth assumption that we made was, or we neglected for the time being, was the supervision complexity. So earlier, all the supervisor would be looking at is one single car. But now, if in the four stages of pipeline version, the supervisor would be monitoring progress of 4 cars in different stages. So obviously, there is additional work to be done. And the fifth assumption we made was overlooking on where we would keep the unfinished cars. For example, after we build the engine of the car, where will we place it so that the guys who are working on the body will pick it up? Or once the guys who have worked on the body of the car or the chassis of the car, where will they keep it, right? So that the guys who are working on the paint would take that and start painting. So that if you try to imagine physically, we need some space where all these unfinished parts would be kept, so that the next stage would can pick them up. Earlier that was not the case, because there was a single line, and the other guys are anyways waiting, right? But here it might not be the case. So where do we keep these unfinished cars? So we need extra space. So all these assumptions we have made, and we said that if we are able to split the car manufacturing into 4 parts, we can get 4 times the throughput. That is the ideal throughput of the pipeline. Now let's move to the instruction pipeline and try to understand it at the actual hardware. Okay, the instruction pipeline, now it's more obvious on the 5 stages or 5 steps that we already discussed. From now on, I'm going to refer the steps as stages explicitly. The first step or the first stage was the fetch stage, where we get the instruction into the IR using the PC and increment the PC. The second step or the second stage is the decode stage, where we are going to look at the content of IR and we are going to determine whether it is an arithmetic instruction or a data transfer instruction or a control instruction. And we'll also identify what are all the operands, whether it's register operands or the immediate operand, right? And which one is source, which one is destination, etc. And we'll also have a question on what to do if it's a branch, right? Because with we don't know whether the next instruction to be fetched is useful or not. So I'm going to touch upon this question, what to do with branch eventually. In the third stage, execute stage, we are going to actually perform the ALU operation, add, subtract, shift, left, right, etc. And for load and store, we are going to calculate the effective address, right? And for the control instructions, specifically for the branch instructions, we are going to resolve the branch if it is equality check or inequality check, greater than or less than, etc. Right? All that check will be done, and we'll know whether we have to continue with the next instruction or jump to the target address. In the fourth stage, the memory access stage, if it is a load and store, we are going to talk to the memory. For loads, we are going to ask the memory to supply the data. If it is store, we are going to give data to the memory and tell it to save it at the address we have given it. The fifth stage is the write back stage, also called register update, is where we are going to update the destination registers. Right? You can take it as a quick recap of what we have seen earlier. Now let's try to pipeline all these stages and see what happens. Okay. So again, we have the timeline, and let's start with instruction 1. So instead of visualizing it as a one single operation, now we'll be visualizing it as 5 different stages. The very first stage is fetch, followed by decode, execute, memory access, and write back. So in cycle 1, instruction 1 would be fetched. In cycle 2, it will be moving into the decode stage, and instruction 2 will be fetched. In cycle 3, I1 will move to the execute stage, I2 will be decoded, and we'll start fetching I3. In the fourth cycle, I1 will be moving to the memory access stage, I2 will be executed, I3 will be in the decode stage, and will start fetching I4. In the fifth cycle, I1 moves to the write back stage, I2 moves to the memory, I3 moves to the execute, I4 moves to the decode, and we will start fetching I5. In the sixth cycle, I2 will be in the write back stage, I3 will be in the memory access, I4 will be in the execute, I5 will be in the decode stage. So extending that, in the seventh cycle, I3 will be in the write back stage, I4 in the memory, I5 in the execute stage, so on and so forth, right? And by the end of ninth cycle, we'll be completing execution of I5 also. Now, if we look at this execution, let's assume that one cycle is taking 1 nanosecond. So effectively, again, cycle a quick recap. It would be the time between two positive edges of the clock or two negative edges of the clock. Here it's 1 nanosecond. In the unpipelined version, where we assume that we will go to I2 only after we complete I1, right? The 100 instructions would take 500 nanoseconds, right? We are going to pick I2 or fetch I2 only in the 6th cycle and fetch I3 only in the 11th cycle, so on and so forth. right? But in the pipeline version, what we are able to effectively do is execute these 100 instructions in 104 nanoseconds. How did we get 104? The very first instruction would be out after 5 cycles, right? But the remaining instructions would effectively take only 1 cycle each. So overall, for 100 instructions, we would need 104 nanoseconds. Now, if you look at the speed up, it would be 500 on top of 104, approximately 5 times. Just like the car manufacturing, where we split it into 4 steps and we got 4 times the throughput. Here too, we split the instruction execution into 5 different stages, and ideally we should get 5 times the throughput. So it's a brilliant idea, right? That's why it's so popular. But let's see what it takes to implement it, right? The reality check here, again, similar to the car manufacturing unit, the assumptions we made here are we did not look at where we are going to keep the unfinished instructions. For example, after the fetch, what we are going to have is the instruction in the IR, right? And what we have after decode are the destination and source register operands, what kind of instruction it is, and all this information, right? So where are we keeping it? The second assumption we made that each of these 5 stages, fetch, decode, execute, memory access, and write back, are taking same time, but that need not be the case. The third assumption we made that uh, is that we have exclusive hardware to perform each of these operations of fetch, decode, execute, memory access, and write back. But we'll soon see that it's not the case. And the fourth assumption we made is executing one instruction is totally independent of another. But we know that it's not true, right? Let's say we are loading a value from the memory into register x10. Why are we loading it? Because we intend to use it in the following instructions. So this instruction is kind of source for the other instructions. Now, how can we execute them in parallel, right? So there are some interesting issues that we are going to look at. And the fifth uh, assumption is, or rather, uh, we ignored that, is the complexity in the control circuitry. Earlier, or the control circuitry was just dealing with one instruction, right? All the control signals it's generating are for only one instruction at a time, right? But now it needs to generate appropriate signals for 5 different instructions at different stages. So a quick point on the single cycle and multi-cycle implementation that we saw earlier. The multi-cycle implementation is naturally leading us to the pipeline implementation of the instruction execution, right? That is the precise reason why I have introduced that in the previous few classes itself. Okay, now moving on, let's try to address each of these assumptions one at a time and see how we can handle them. The very first question we have is, where do we keep the unfinished instructions? To answer this, let's try to discuss a case on what would happen if we are not going to handle this issue. Okay, let's consider the decode stage and execute stage. We all know that the output of decode stage would be the input of the execute stage. Now let's say the instruction I1 is add x1, x2, x3, and let's say that x2 and x3 have values 10 and 20. So the output of decode stage would be 10 and 20, let's say by the end of cycle 2. It means that we have fetched I1 in cycle 1. By end of cycle 2, the decode will be ready and it will be driving the values 10 and 20 to the execute stage. In cycle 3, what we actually expect is that execute stage or the ALU would be working on these values 10 and 20, will add them, and the resultant value 30 will be placed, will be ready by the end of cycle 3. But what's happening in cycle 3 is, let's say we are trying to decode another instruction. Here it's add x5, x6, x7, and let's say the values of x6 and x7 are 30 and 40. Now somewhere in between cycle, during cycle 3, right, the output of decode will change to 30 and 40. I have deliberately overwritten the values to give a feel on what would be the execute stage looking at. Will it look at 10 and 20 or 30 or 40, right? Or it can be 10 and 40 and 30 and 20 also. We don't know. Or it can be some other junk value. Now, how do we expect it to add 10 and 20 if the input are not held stable, right? So the output of execute stage by the end of cycle 3 is kind of indeterminate. This is what would happen if we are not able to carefully handle the data transfer from one stage to another stage. Now let's see how we can handle it. The most straightforward answer is to introduce a small buffer, right? What is a buffer here? It has let's say 2 inputs and 2 outputs in this case, and let's say the values to it to its inputs are 1 and 2. It will sample these input only at the beginning of the or only during the rising edge of the clock cycle, and the output will remain 1 and 2 during the next clock cycle. It means that till the next rising edge. So you know, you all know what this is. It's an edge triggered flip flop, right? Its output will remain same as long as the clock trigger edge does not move from, let's say, the positive edge to negative or negative to positive edge, right? So let's see how this will help us in our execution now, right? A quick point is in between, if the values of the inputs to this particular flip flop changes to 3 and 3, the output will still remain 1 and 2. That is the key here, right? Now let's look at the execution of I1 and I2 here. In cycle 2, the decode stage will place 10 and 20, right? At the beginning of cycle 3, this would latch on to those values, and 10 and 20 will be held in stable state as inputs to the execute stage. And the inputs during cycle 3 for this particular buffer can change to 30 and 40, right? And this particular buffer will latch on to 30 and 40 only at the end of cycle 3, means the rising edge here. But in the meantime, the execute stage will work on 10 and 20 and produce the value of 30. So this is how we can handle the data movement between the stages. Now let's try to extend it for the other stages also. We place one buffer between each of the stages of the pipeline. In one cycle, the inputs to these buffers would be driven by the previous stages, and in the very next cycle it would be driving as input to the next stage. In this way we can uh, stabilize the data flow between different stages of the pipeline. So it's all good, right? We solve the problem, but what is the side effect? Nothing comes for free, right? The side effect is the cycle time. Now we should account for the buffer's time also. So earlier, let's say fetch stage used to take 1 nanosecond. Now we should account for the delay of the buffer also, right? Let's say if the buffer is taking zero point 0.1 nanoseconds, now the cycle time would be 1 plus 0.1 nanoseconds. What it means is, earlier we would have run this particular pipeline, right, at 1 gigahertz, but now the frequency reduces to 1 upon 1.1 gigahertz, right? That's the impact on the frequency. But if you want to look at the absolute time, earlier 100 instructions were taking 104 nanoseconds, but now if we look at the actual time, the first instruction would be out after 5.4 or 5.5 nanoseconds, and later on every instruction would come out after 1.1 nanosecond, right? Now if you look at the speed up, earlier it was 500 upon 104, but now that 104 would be increasing. What that implies is the speed up will reduce. It will no longer be 5, the ideal pipeline speed up. Okay. Now this is an important factor that determines on how deep we can pipeline. So what we are currently looking at is only 5-stage pipeline. Now can I make it 7-stage or 8-stage or 10-stage pipeline? The more the number of stages, obviously the buffers will come into the picture and will not get enough speed up. So when I move from 5-stage pipeline to 10-stage pipeline, right, what I expect is uh, the throughput would be doubled. But now because we have to include the buffer time also, it will no longer be the case. Okay. Moving on, the second assumption we made was assuming that all these stages will take equal time. But we already know the internal circuits that are needed for the fetch, decode, execute, memory access, and the write back. So it's highly unlikely that they all take equal time, right? We assume that all of them might be taking 1 nanosecond, but what if the execute stage needs 1.5 nanosecond? In that case, the new cycle time would be 1.5 nanoseconds. What this implies is the remaining 4 stages, even though they have finished their work in 1 nanosecond, the remaining zero point 0.5 nanoseconds, they will not be able to make any progress. It means that they cannot work with the next instruction. They have to wait. Now, again, if you calculate the total time that would be taken by 100 instructions, right? The first instruction would take 5 times 1.5 nanoseconds. Now, for simplicity, I'm ignoring the buffer time here, right? The first instruction would be out after 7.5 nanoseconds, and the remaining 99 instructions would be out for every 1.5 nanoseconds, right? So again, the speed up will drop further from the ideal speed up. And what if the memory takes 2 cycles? Then, right, the new cycle time would be 2 nanoseconds. So accordingly, the speed up will reduce further. So we blindly take the new cycle time as 2 nanoseconds, or is there any optimization possible? That is a discussion I'm going to touch upon probably at the later end of this module, right? To give a quick hint, can I split the memory stage itself into 2 stages so that I can get them working as 2 stages of 1 nanosecond each? Is that possible or not? If it's not possible, how can we handle? If it is not possible, what it means is, for the fetch, decode, and write back are taking 1 nanosecond, execute is taking 1.5 nanosecond, and memory is taking 2 nanoseconds. It's called unbalanced pipeline stages, right? And obviously the throughput will be far from the ideal throughput, because every other stage needs to wait for the slowest stage to finish its task. So in this regard, I would like to point you all to an interesting, very intuitive example in sorry, from the textbook Computer Organization and Design, Rescue Edition by Patterson and Hennessy. Do go through it. It's very well explained, and you'll see the impact of unbalanced stages on the throughput. Okay, we can discuss it further in the upcoming live session if you want. Moving on, the third assumption we made was assuming that the hardware for each of the stages is exclusive. Now let's try to address that. We expect instruction 1 would pass on from one stage to another, fetch, decode, execute, memory, and write back. And instruction 2 would be looking like this. So when I1 is getting decoded, I2 will be fetched. In the same way, when I1 is getting executed, I2 would be decoding, and I3 will be fetched, so on and so forth. In the fourth cycle, right, we are going to see that I4 will be fetched, I1 will be in the memory stage, I2 will be in the execute stage, and I3 will be in the decode stage, right, so on and so forth. Now if we closely observe what's happening in C5, this fifth cycle, as part of execution of I1, we will be updating some destination register, right? But in the same cycle, as part of execution of I4, we are going to read from the register file, right? In the decode stage, that what happens, we identify which registers we need to read, and we are going to read from that register file. So in this cycle, we are communicating to the register file both for writing the data and reading the data. Now because it's a single hardware unit, there is a conflict. How can it handle both of them in the same cycle? So one of the most popular implementation is, we will make the writes during the first half of the cycle and reads from the register file during the second half of the cycle. That is the reason we have dedicated read ports and write ports to the register file. But what does it mean? We are writing to the register file in one half of the cycle, we are reading from the register file in another half of the cycle. It implies that the register file needs to work twice as fast as the other stages. For example, if the other stages are taking 1 nanosecond, right, in the write back stage or in the decode stage, within 0.5 nanoseconds, the first 0.5 nanoseconds, we are going to update the register file. In the second 0.5 nanoseconds of the same cycle, we are going to read from the register file. That is also one of the reasons why we keep the number of registers short, because if the registers are less, then the registry file hardware would be small and we can get it working faster. Okay, so making the register file faster, we are able to address one issue of accessing it in the same cycle. For reading purpose for I4 and for writing purpose for I1, right? Now let's see if there are any other issues. So here we have I1, I2, I3, I4, I5, I6, so on and so forth, right? Now during the fourth cycle, if we observe, I1, if it is a load instruction, will be trying to contact the memory to get the data. In the same cycle, we are contacting the memory with the IP, sorry, or instruction pointer or the PC of I4 to get that particular instruction and place it in the IR. So in cycle 4, we are trying to access the memory, right, as part of execution of two instructions, I1 and I4 again, right? Now the one of the straightforward thing from the previous slide is, can we make the memory working faster? During the first half, it will try to service one request. During the second half, it will try to service another request. But it's not possible because memory as such is very, very slow, right? We'll understand why it is very slow in the next module anyways. So the whatever we did for the register file will not be applicable here. Now let's see how we can execute if the memory cannot be accessed by multiple guys at the same time. What happens is, in the first three cycles we are going to fetch I1, I2, I3, right? In the fourth cycle, I1 will be in the memory access stage, I2 will be in the execute stage, I3 will be in the decode stage. Because the memory is busy servicing I1, we cannot access it, so we cannot fetch uh, I4. So what we do is nothing. Basically we need to wait, right? When we wait, we create a gap in the pipeline. We call that technically as a bubble, right? Bubble means we are not doing anything in that particular cycle. So in cycle 4 we are not able to fetch I4. Now can I fetch I4 in cycle 5? No, because I2 will be in the memory stage. So again I will introduce one other bubble. So even though you see 5 bubbles here, actually whatever we did not do in cycle 4 will be trickling down to the decode stage in cycle 5, trickling down to the execute and memory access and write back. So that's why we see 5 dots or 5 bubbles. Basically it will reflect as one cycle of no work. Okay, so the same thing would happen in cycle 5 also. Can we fetch I4 in cycle 6? No, because I3 will be in the memory stage. So again there will be one more bubble introduced into the pipeline. I can only fetch I4 in the 7th cycle. What it means is, effectively I can execute only 3 instructions for every 6 cycles. Now the performance has dropped quite drastically. Earlier we were able to uh, execute one instruction every cycle, but because of this memory issue, right, we are able to execute one instruction only after every 2 cycles effectively, right? So the performance dropped by half. We cannot accept it. What is the way out is, the designers thought, why not place the text segment or the instructions separately and the data segment separately. Accordingly, we have the instruction memory and the data memory. All the text segment will be placed in the instruction memory. So instead of imagining the memory as one big chunk, now imagine it as two chunks: instruction memory and the data memory. What happens with that is, in cycle 4 we are going to access the data memory to load or store the data. In the same cycle we are going to contact the instruction memory to fetch the instruction. So because there are two physical modules, there is no conflict there. So we are able to get better performance. So this constraint of trying to access the same hardware multiple times in the same cycle by different instructions is called structural hazard. Now what it means is, there is a conflict in the shared resource, shared hardware. The term hazard means any condition that obstructs the smooth functioning of the pipeline. What we have seen is the structural hazard, structural in the sense the actual availability of the hardware. We are going to see some more hazards also. Now what happens if we don't handle the hazards is, the throughput of the pipeline implementation will drop very badly. Why did we come to pipelining to begin with? For a better performance, right? For the better throughput. But what's the point if we are not able to achieve it because of these hazards? So accordingly, we need to carefully handle each of those hazards, right? And try to clear them up, like we did for the register file and like we did for the memory. I will leave it to you to see if there are any other structural hazards when we are trying to execute these 5 stages of the instruction execution. just think it over and see if there is any more conflict at the hardware. Okay, with that I'll pause this lecture. Right, what we have seen in this lecture is trying to get the pipeline implementation of instructions in a more practical way. Right, we introduced the interstage buffers, or the pipeline buffers they are called, between each of those pipelines, where we are going to store all the intermediate data. Right, and we have looked at the structural hazard. We are going to look at some more interesting issues to get the pipeline up and running. Okay, but that's for the next lecture. I'll pause now. Thank you.